This is a video tutorial series about the Automotive Open System Architecture, or AUTO-SAR. The ultimate aim of this video tutorial series is to support automotive engineers to improve the AUTO-SAR competencies through short technical videos. Here in this first part, Introduction to AUTOSAR World, we are trying to explain the necessity of an open architecture for automotive industry and its basic architecture. If you need any clarifications for the points that we are putting forward, please add comments in the commenting section and we are very much happy to reply you at the earliest. Let us start the journey through the AUTOSAR world. Automotive Open System Architecture, or AUTOSAR, is a worldwide development partnership of vehicle manufacturers, suppliers and service providers from semiconductor and software industries. The collaboration between various partners enables the reuse and exchangeability of software modules between original equipment manufacturers and suppliers. Its main aim is to standardize the software architecture of electronic control units or ECUs and thereby improves the quality and efficiency of the electrical and electronic architecture in the entire vehicle system. AUTOSAR Consortium defined 5 different types of partnership. Each partners are assigned with the appropriate rights and duties. There are 9 core partners and these partners work together to define the new standards that supports the future car application needs. Here we lists the different types of partners and their rights and duties. However, we are not explaining about this, as these informations are easily understandable and straightforward. You can go through this slide to understand the different rights and duties. Now let us try to understand the main goals of the AUTOSAR architecture. The main goal behind this standardization is to create softwares that are widely independent of hardware. This means, the AUTOSAR architecture enables the reuse of the software in multiple microcontroller platforms. Second idea behind this AUTOSAR architecture is the parallel development of the softwares, by decoupling the software functionalities. AUTOSAR architecture allows the OEMs to categorize their final requirements based on the multiple functional domains and share it across multiple vendors. Then these vendors can independently develop the software for the assigned functionality without even worrying about what others are doing. Ultimately, this parallel development process reduces the entire product development time and the time to market. Third goal of AUTOSAR architecture is to reduce the cost and improve the quality of software by reusing the different software modules from already existing softwares. AUTOSAR provides a set of specifications that describes the structure of basic software modules and also defines the application interfaces between these basic software modules. In upcoming slides we would see what are basic software modules. So when we develop an automotive software application based on AUTOSAR defined standard, that software can be portable in vehicles of different manufacturers and electronic components of different suppliers. This ultimately reduces the expenditure for research and development. These are the main topics on which AUTOSAR Consortium is working on: architecture, methodology and application interfaces. AUTOSAR architecture provides a structured integration platform for hardware-independent software applications, with the help of AUTOSAR basic software of BSW. Methodology defines the data exchange formats or description templates, to enable a seamless configuration process of the basic software stack, and the integration of application software in electronic control units. Application interfaces provides a standard specification of interfaces from all functional domains in terms of syntax and semantics, and that should serve as a standard for application software development. We will see all of them in details. AUTOSAR methodology defines the work product flow for developing an ECU software, and it also defines the dependencies of different activities on work products. We will try to brief the main activities that are involved in the AUTOSAR-based electronic control unit development. Main activities are design of an abstract system, virtual functional bus development, system design, software component design, development of basic software modules and the integration of AUTOSAR electronic control units. Before going into the details of these different steps, we will look into the data exchange formats. As we already discussed, AUTOSAR is a partnership business. There must be a standard format for sharing the formal data between the participating members. In order to standardize the formal data exchange, AUTOSAR defines a standard templates called AUTOSAR Schema. These formal data description is based on XML file format, and in AUTOSAR terms these files are called AUTOSAR XML or AR-XML. If we look into the entire design and development stages of ECU, there are different kind of AR-XML files available with different set of information. To simplify, we can consider AR-XML as a database that holds the information about the system constraints or software components or details about ECU resources. System constraints includes topology of the network in the vehicles, information about different software modules or software components that is to be present in final ECU, and the grouping of software components belongs to same functionality. Software component details includes details like data type of signals involved in the communication and the connection details between multiple software components. ECU resources includes hardware-specific details like details of processing units, memory, peripherals, and even contains the hardware pin details. We think this much basic understanding are more than enough for going further to understand the AUTOSAR methodology. Let us try to understand each steps in the AUTOSAR methodology in detail. The abstract system design is the first step in the design process that focuses on the development of a functional architecture. In this activity, an abstract system description is developed, which represents the overall vehicle function in a functional or abstract view. This functional description might contain information regarding the topology and the mapping to ECU, and also it serves as an input for the development of the virtual functional bus. However, the abstract system design is an optional activity. Next step is the design of virtual functional bus or VFB. In case, if the abstract system design is not done, the development of the vehicle system directly starts by defining the virtual functional bus or VFB. This concept allows the system engineer and software component engineer to model the entire vehicle system by defining different software components and the virtual communication paths between these software components. We can consider software components as a simplest form of an application with certain functionality. During virtual functional bus design, multiple software components are connected through a common point of interaction, called ports. A port of a software component is associated with port interface, and then the port interface controls what can be communicated through ports. We will give more details about different types of ports and port interfaces when we give training about the application software component design. At the VFB level, it is not yet clear how the electronic control unit will later be distributed and connected to each other in the real vehicle, but it is a helpful test environment in the architecture development phase. In short, VFB provides an abstract view of all the software components of the final system, and it also enables the development of software. Software component design. The software components can be implemented according to the definitions available in the virtual functional bus. Based on the external components connections defined in the VFB, the internal behavior elements of the software can be defined to implement the software. Internal behavior elements are used to define how the software component will interact with runtime environment or RTE during runtime. Internal behavior elements mainly specify the runnable entities, RTE events, exclusive areas, and data access definition. The implementation of a software component can be done independent from the configuration of the ECU. Next step in the workflow is system design. In system design, the information from VFB design is redefined into a detailed system by defining a topology between multiple ECUs and by deploying software components across the multiple ECUs. The communication matrix, which contains details about the message frames, are also derived in this system design stage. System description AR-XML is the output from system design, and it contains the complete details about the software component, network topology, and communication matrix which is to be assigned across multiple ECUs. Next step is basic software design and the ECU integration. AUTOSAR basic software consists of different dedicated software modules or software stack that serves different functionalities like communication, memory management, mode management, diagnostics and error handling, etc. The configuration of basic software module can start once the network matrix for the specific ECU is available. From the System Description ARXML, which contains details about multiple ECUs, ECU extract of a specific electronic control unit is given as an input to start the ECU integration activities. This is a pictorial representation of the process. Here you can see the different types of ARXML files that are involved in both system design and ECU design phases. So these are the main steps that are involved in the AUTOSAR methodology and that helps the development partners to foresee all support activities, usage of different descriptions files and use of tools in AUTOSAR. We can now move on to the architecture details of AUTOSAR layers. The AUTOSAR software architecture is a layered architecture that supports the realization of functional requirements into an electronic control unit. The main goal of this layered architecture is to abstract hardware components from application layer. The layered architecture consists of three different layers: basic software, runtime environment or RTE, and the application layer. Let us try to understand the basics of each layers. Basic Software Layer or BSW layer is responsible for managing hardware resources and providing common services for application software. BSW layer is again divided into three different layers. They are Microcontroller Abstraction Layer or MCAL, ECU Abstraction Layer and Service Layer. The Microcontroller Abstraction Layer is the lowest software layer in BSW and provides direct access to all the on-chip microcontroller peripheral modules and external devices, which are mapped to memory. This MCAL layer makes the application and basic software layer independent of the underlying hardware platform. We can again classify the Microcontroller Abstraction Layer into different set of drivers based on the functionality. These driver provides a software interface to hardware devices. Few of them are microcontroller drivers, memory drivers, communication drivers and input-output drivers. As the memory layout and the architectures are different for every microcontroller has its own MCAL drivers. MCAL driver needs to be configured based on the requirement for the specific ECU. For example, microcontroller may feature 2 or 3 inbuilt CAN controllers, however the application might require only one CAN hardware to be configured. So the configuration of these MCAL fully depends on the application requirements. Next layer in BSW stack is ECU Abstraction Layer. Main task of ECU Abstraction Layer is to make the higher levels independent of ECU hardware. The ECU Abstraction Layer offers uniform access to all functionalities of an ECU such as communication, memory or all input and output, regardless of whether these functionalities are part of the microcontroller or are implemented by peripheral components. Next is Service Layer. Service Layer is the highest layer of the basic software and it contains multiple modules that provide background services for applications, runtime environment, and basic software modules. Service Layer provides different types of background services such as operating system functionality, vehicle network communication and mode management services, ECU state management, diagnostic services, etc. Now we will see AUTOSAR Runtime Environment or RTE. RTE is a layer between application layer and basic software layer. This layer abstracts the application layer from the basic software. The AUTOSAR software components communicate with other components which are present in the same ECU or in the other ECU through this RTE. RTE also provides communication and scheduling services to software application. It basically controls the runtime behavior of the application layer and implements the data exchange between multiple software components. The purpose of the RTE layer is to make application software independent of a mapping to a specific ECU. This permits software components to be reused or relocated to different ECUs in a vehicle. The final layer in the architecture is Application Layer. In AUTOSAR architecture, Application Layer is the topmost layer and it contains applications that are specific to that particular ECU. These applications are represented as multiple AUTOSAR software components or SWCs, and these constitutes the simplest form of an application with certain functionality. Multiple software components that are grouped and interconnected logically can be considered as a composition. AUTO-SAR infrastructure capabilities make software components independent from the type of microcontroller, type of ECUs, location of the other SWCs with which the component interacts. As we already said, these software components are connected with the help of well-defined ports. These ports facilitate communication between the software components as well as with the AUTO-SAR basic software. To be able to connect ports, the interfaces of the two ports must be compatible. There are two types of interfaces: sender-receiver interfaces and client-server interfaces. A sender-receiver interface supports message-based communication, while a client-server interface supports a remote procedure call style of communication. We will have a separate training session that explains how to design a software components. Here is the pictorial representation of AUTO-SAR-based electronic control unit in a vehicle network. We hope that you understood the basic concept of AUTO-SAR and ready for upcoming video sessions. If you have any questions regarding any points, please do comment us. We will reply you at the earliest. We will be covering different BSW stack in the upcoming videos. Subscribe to our channel and do share with your friends. Don't forget to click on bell icon to get notification about new videos. Also follow our Facebook page to get technical informations from automotive field and other interesting topics. Thanks for watching.